Thank you very much, Mr. Chairman. And today I would like talk about last results in our laboratory about the shape memory alloys. Shape memory alloys are a wide class of material characterized by the ability to recover the initial shape also after high values of deformation. And we can have two kinds of shape memory alloy. The first one is the traditional one, where the initial shape is recovered by heating the material. And the second one recover the initial shape without any heating. This is due to the critical temperature. In this case, is a temperature higher than the environment one. In the second case, it's lower than the environment one. In many works, we can find that at low values of deformation, we have the presence of a microstructure often named as austenite, and at high values of deformation, we have the presence of martensite. Austenite and martensite aren't the traditional iron-based phases, but are named in this way in literature. And in second stage, we have the transition from austenite to martensite under the effect of external loads. In this case, the martensite is named as stress-induced martensite. Sometimes the presence of this plateau is modelized as this in linear manner, and starting from 0% of martensite to 100% of martensite, in this stage, sometimes the variation of a microstructure is linearized. It means that at the middle of the stage, we have the 50% of austenite, the 50% of martensite. So this is the start of the value, and we perform some kinds of test. The first one is a simple test tensile test, and you can see that the presence of plateau is not a very plateau, because we have a sort of slope of this stage, and then we have the austenite and martensite one. So the suspect is that is not linear, the transformation. Okay. So this is the questions aimed at our work. Which is the real microstructure evolution under the cycling deformation? Which is the influence of a microstructure on mechanical cyclic behavior? And which is the influence of a microstructure on tensile crack micromechanisms? For this, we produced a material using a vacuum furnace like this with a crucible in yttria, because it's very stable high temperature, avoided the presence of any oxide. And using a graphite mold, we realize, for example, this ingot. This is investigated the chemical composition of the alloy. It's a near equiatomic alloy. This is the final microstructure. After the process, we produce a mini dog bone tensile test specimen, able to be used in our patented tools that is able to schedulate different values of deformation. Keeping this deformation is able to put the calibrating length, for example, on the chamber of XRD diffractometer in order to perform the diffraction test necessary to evaluate the real phase composition. Then we produced other kinds of spacemen in wire shape in order to compare the mechanical property. So this is the first results you can see in tensile test. We have the presence of austenite. Here started the formation of the tensile of martensite, the transformation starts here. And in unloading condition, we have a behavior that is very different, but the initial shape is recovered. For this reason, we schedulate some values of deformation in loading condition and in unloading condition in order to perform the diffractometer tests. This is the first results. This is the spectrum obtained in undeformed shape. We have the presence of a peak at these values of diffraction angle, and other one I values. Analyzing the spectrum, is possible to say that the cell is a cubic cell characterized by nickel atom on the edges of the cell, and the titanium atom is inside. Then, higher values of deformation, 10%. We have the spectrum of the martensite. You can see here the peaks are completely different, and the peak is moved in versus high values of angle, diffraction angle, and the cells are different. We have the presence of a monoclinic lattice characterized by the titanium atom, which moves from the center of the cell to the edge. So, analyzing three different deformations in one cycle, we can see the first spectrum. This is the main peak. We perform the analysis on the first peak because the other one are redundant. And after 10% of deformation, the peak move here because it is changed the microstructure. And then in a loading condition, we recover the same values of the angle at the maximum values of the peak. The intensity is changed because I think that after one cycle, inside the material, we generate some defects. So this is the mechanical stress-strain relation between in one cycle. And you can see, for example, that at 5% of deformation, we have different levels of the stress. Okay, in this case, we have this point that is inside the second stage, and this one is inside the second stage too. In terms of spectrum, you can see that in loading condition, we have the presence of austenite, and the martensite is lower, and vice versa. In a loading condition, we have a big presence of the martensite, a low presence of austenite. This is the effect of this hysteresis in terms, not mechanical terms, but in terms of microstructure. Why change the microstructure? How we can take into account the variation of microstructure during the deformation? In a recent work, we postulated the presence of the energy that is a drive of this kind of phenomena, and in differential form is depends of the deformation, and this is the in many works in literature using only this dependency. But we postulated the presence of austenite volume fraction and martensite volume fraction is influence of this kind of phenomenon transformation. So the differential of the energy, the first part is characterized by a constant C and depends on the variation of deformation. Plus, we postulated another contribution of the variation of the austenite on the austenite, a sort of referred variation of the austenite on the austenite. In the same way, we put the contribution of the martensite with the minus sign because the austenite transforms in martensite and vice versa. At the equilibrium, this equation must be 0. And integrating the equilibrium state, we have this relation where it's trivial to obtain a true relationship, very easy to use, of Martensine quantity in function of the epsilon and the austenite one as a complement to 1 of volume fraction. In this case, here you can see the experimental results and model how are in agree in loading condition and in unloading condition using these parameters C and D. You can see that C is 1 and D change in 700 in loading condition and change in 70 in unloading. It means that the parameter D takes into account the hysteresis, microstructural hysteresis. Performing the same test in 10 cyclic, 50 cyclic, and 100 cyclic, you obtain these results. C changes from 1 at the first cycle to 0.9 at 10 cycles. This is the values for the 50 cycles, and this is the value of the 100 cycles. And you can see that the values D is always this and this in loading and unloading condition, and is not influenced by the cycle. It means that C takes into account the cyclic, and D the hysteresis. Plotting the parameter C in the double logarithmic scale, you can see a behavior similar to the Wheeler one. So, analyzing the first values of deformation, you can see that at 0% of the deformation we have this peak that moves a high values of angle when the deformation is 2.5%. At 3.3, the values is almost the same, but the variation of austenite and martensite is beginning. And at 5%, you can see that the peak is lower in intensity because it's changed. We have less austenite than the past. Analyzing the spectrum, you can see that in undeformed condition, this is the cell parameter, increase to these values. After these values, we have not an increasing of the cell parameter of austenite, but a collapse of this microstructure in this, generating this angle, okay, and changing the cell parameters like this. Calculating the position of the right atoms, we can see that from this to this, we have an increase, an excess of deformation. Around 3% of deformation. What it means, looking at the relation between sigma epsilon, 3.3 is here. The excess of deformation implies a collapse of the slope of the curve due to transformation of the austenite in martensite. This is our opinion on the presence of the plateau. It's a strange plateau because the slope is minus than the slope of austenite in martensite 2. In order to find a relation between the stress-strain curve, taking into account the martensite austenite transformation, we propose this simple form. It's a way that 1 minute. It doesn't work this form because the austenite, not all the austenite participate to the increase of mechanical stress, but part of this use the energy in the transformation. So, eliminating the quantity of the austenite that is transforming in martensite, you have a different form like this for austenite and martensite, and where the austenite and martensite is calculated and the derivative is easy to obtain, and the results are this. For the first cycle, experimental and model, these are these. after 10 cycles, after 50 cycles, and after 100 cycles. Using a different spaceman, using a wire, we perform the same test 100 cycles like this, but we have no differences using the mini dog bone, not standard test. And the question is always the same. If here I have a quantity of martensite which is not able to recover in austenite, this is the loss of the memory, part of the memory effect, which is the difference from the martensite able to recover in austenite and martensite that are stable martensite. In terms of spectrum, it's impossible to find this, because the peak is always the same, and you can change the amplitude, but the position is almost the same. So we try to perform another test. The test is performing one cycle and then a traditional test up to rupture. Taking another wire, 10 cycles, and then test up to rupture, we obtained different crack surface. This is the first surface. You can see that we have a shear zone, and this zone is characterized, it's a flat shape due to the triaxiality. After 10 cycles, it's almost the same. I don't report this. After 50 cycles, we can see that the internal part seems to increase the importance than this. After 100 cycles, seems to be near to flat. High values of deformation. In one cycle, we have a presence of diffusion dimples. After 50 cycles, we have a presence of a short region of coalescence. After 100 cycles, we have the presence of real secondary crack, micro secondary crack like this. It could be due to the defect generated inside of martensite. It could be an answer. So, according with the experimental results, we can see that the austenite martensite and inverse transformation are not linear. The stress strain behavior shape depends on the austenite martensite volume fracture, not only on deformations. And after 100 cycles, we have a presence of martensite that are not able to recover the shape, increase the presence of secondary cracks. Thanks for the attention.